Hello, everyone. My name is Mohammed, and I'm here today with my colleague, Duarek. Today, we are going to talk about training models at Facebook scale with PyTorch. We are going to talk about the challenges of training at Facebook scale and how PyTorch enables us to address some of these challenges. Duarek will talk about some of the PyTorch features that made this possible and few case studies that are deployed in production. First, let me give you a quick update on PyTorch growth over the past 18 months. I hope that a lot of you here in the audience are using PyTorch. Thanks for its ease of use and good documentation. We have seen significant growth over the past 18 months in PyTorch usage. This shows up in number of paper implementation grouped by framework, as you can see. We use PyTorch at Facebook for major training workload, such as computer vision, NLP, machine translation, speech recognition, and ranking and recommendation systems. Training at Facebook brings in interesting challenges. To give you an idea of the scale of our models and training workload, at the beginning of 2018, 30% of the data stored in Facebook warehouse was used in an ML in training machine learning models. Today, this number is 50%. This, along with the fact that the data warehouse has doubled in size over the last year, for those of you doing the math, that means the data used for machine learning has tripled over the past 3 years. Over the past year. Over the last 18 months alone, the number of engineers that are using our platform to train new models has doubled. At the same time, each engineer increased the number of workflows or the experiments they are training. And finally, the complexity of the models increased such that we saw 8x increase in the amount of compute to train these models. What's getting in our way for better experimentation? As we mentioned before, data aggregate is getting bigger, but even for single experiment, we are using more data. As an example, in one of our recent published CV experiment, we went from training on 1 million images to 3.5 billion images, and currently we're exploring training on 10 or 100 billion images. Here's what else is getting in our way. The models are getting more complex, way more complex. As an example, we went through 4 generations of our ranking and recommendation models, with each generation bringing at least 10x model complexity over previous generation. The complexity is reflected in more training time. You can see from this graph, our ranking and recommendation system has gone through 4 generations, from decision tree to complicated deep learning models. As you can see, we went from training CV models from few days to over 2 weeks now. Imagine how long it would take to train our internet scale videos models. Models are getting more complex as well, which impact the throughput or number of examples we can consume per a single training instance. As you can see, the QPS per trainer has been decreasing over the time, indicating increased model complexity. With all the scale in data, weekly active users, and model complexity, we have a really large scale challenge. Tens of billions of training examples, models that are larger than the size of a single machine in terms of the model size, hundreds of experiments run competing for resources, and more than 1,000 different production models. The scale challenges are impacting multiple layers of the stack. At the foundation, we need to scale our compute, network, and storage capabilities. The platform needs to scale its capabilities and flexibilities to support new cases as well. The number of developers using the platform has increased significantly. The models are scaling in terms of compute complexity and model size, where models are growing from megabytes in size to even terabytes in size. And we are using more sophisticated algorithms. ML training is inherently less reliable. In addition to the experimental nature of the jobs, the number of machines required to run a single large-scale distributed job impact the reliability. Distributed training uses gang scheduling, which means resources are required all or nothing. A single machine or node failure in the system would cause the whole job to fail. As we are running these large-scale ML jobs in data center environment, failures are inevitable. The gang job reliability is a function of the job duration and the gang size. Remember, these jobs are running for from days to weeks, so they're running for a really long time. and they're using hundreds of machines. You can see this from the graph, that the larger a gang job is, the less reliable it will run as we progress through time steps. So far, we have seen that ML training has many challenges, from scale to reliability. ML training has also scheduling challenges. Unlike data pipelines, majority of ML jobs are ad hoc. The long-running nature of these jobs makes demand prediction and control a challenging task. Since these jobs are experimental in nature, predicting the ROI is very hard to estimate. This, combined with sublinear scaling and the huge scale, makes it very easy to waste resources. We run multiple training hardware and different generation in each hardware in our data center. We have training on CPUs, GPUs, and even custom ASICs. ML workload is similar to high-performance computing workload as well. HPC workload is sensitive to hardware types and generation. This makes scheduling a more complex challenge than just allocating X number of GPU memory or Y number of CPUs per task, since it needs to take all these constraints into account. So far, we took an overview of the many challenges at training at Facebook scale. Now Dwark will do a deep dive into some of the features in PyTorch that helps us address some of these challenges. Thank you.
Thanks, Mohammed. I'm Dwark Rajagopal, and I'm going to be talking about PyTorch features. In order to drive research to production transition, we built TorchScript. This is about efficiency and performance. TorchScript is an optimizable subset of the Python programs. There are three main benefits. It removes Python dependency in production deployment, preserves the approach of developing models as programs, while getting the advantage of compilation paths for perf optimization. This subset contains all the building blocks necessary to build models, like tensors, fundamental ops, traditional language features such as control flow with statements and loops. With one annotation, you can transform all this program to a graph. Then you can take this graph and optimize it to target different backends and get the speeds that you need for inference. Because TorchScript is a subset of Python, so if something isn't working and you want to debug further, you remove the script call and debug your model directly in Python. You can see the API is really simple. You write just regular Python with subset of Python that TorchScript supports, and then with one annotation, you can convert this into a graph. It has really good documentation that tells you what are the supported features and what is it not. The problem raised by the community is that oftentimes we don't preserve or maintain semantic meanings to tensors. It can cause accidental alignment issues or accidental broadcasting issues. We introduced a new feature called name tensor, which explicitly names the tensor. This approach promotes type and can make developers' lives so much easier. This way, the code is much more readable and maintainable by retaining the semantic meaning to the tensor. In addition to supporting Python and C++, we also added experimental support for Java bindings. New bindings allow you to invoke TorchScript models from any Java language, from any Java program. Note that Java bindings are only available for Linux for this release and for inference only. We expect support to expand in subsequent releases. You can see the code snippet on how to use PyTorch within Java. So TensorBoard. To help developers acquire deeper model understanding, we have TensorBoard for PyTorch. It's a tool fully integrated with PyTorch to allow users to directly visualize model graphs, histograms of weights or other tensors, images, text, embedding projections, 3D points, and mesh for the PyTorch models. This work is done through strong collaboration with Google TensorBoard team. Another exciting developer tool we launched in PyTorch 1.3 is called Captem. It aims to solve model interpretability challenges. Captem consists of a library and a UI tool. Captem library provides a number of gradient-based attribution algorithms and a visualization tool for model debugging and understanding called Captem Insights. For example, Captem Insights in the screenshot can help us debug which tokens in the text are important for prediction. The magnitude of attribution reflected in the color ranging from blue, which is very important, to red, which is least important. The intensity of the color signifies the strength of the signal. In addition, Captem and TensorBoard can be interoperable. We are planning to create Captem plugin for TensorBoard in the future. With TorchScript and PyTorch JIT, it also enables us to target mobile devices. This allows you to do an end-to-end workflow from eager mode to deployment on iOS and Android with no need to convert to another runtime. We wanted deploying to mobile devices to be as natural as any other device, such as server. PyTorch Mobile supports any TorchScriptable model and out of the box provides pre-built binaries for iOS and Android with support for 8-bit quantized libraries like QNNPAC, FPGA at release. We support a wide range of quantization techniques, all the way from dynamic quantization that you can use for like something like an RNN to quantization of training that you can use during your network training. Building for scale. PyTorch gives you the flexibility of writing imperative programs and translate this into a graph. You can take this graph and you can optimize for different types of hardware backends. And the technology that enables this is PyTorch JIT. So this PyTorch just-in-time compiler enables you to target different backends, including XLA, Glow. PyTorch also integrates with the state-of-art libraries like MKLDNN, cuDNN, QNNPAC, and FPGA. Now let's look at the case studies in terms both for elastic and model parallelism. As Mohammed talked about earlier, unlike data pipelines, machine learning is an experimental. It's a long-running job, and you don't have an ROI for each job. So demand control and prediction is very hard. Sublinear scaling and huge scale makes it very easy to waste resources. So how do we fix it? Would it be nice to have a fault-tolerant and an elastic distributed PyTorch? Comes in PyTorch Elastic. We open source recently. We use it internally to train large CV models with 10 billions of images from 256 to 1024 GPUs in an elastic way so that a single job failure does not impact the progress of the job. So we can run this on a non-HPC cluster in data center where the failures are normal. We can also run this on mission control workload and also use for dynamic capacity. Oftentimes, we start training with whatever capacity you have and keep adding machines whenever they become available. So it impacts developer productivity as well. This is an example of how it works. You specify the number of min and max nodes that you're targeting and write your model using PyTorch Elastic APIs. This allows automatic checkpointing, recovery, handling node failures, handling automatic node appearing, and node coming back, and it does all this transparent to you. Now let's take a closer look under the hood to see what are the key components inside PyTorch Elastic. One key mechanism happening here is the rendezvous mechanism. So this is basically our library, our method that gives you the membership changes, new machines coming in your job or disappearing from your job that causes failing. It also acts a barrier. So it waits until you request a minimum number of machines before you can progress and dynamically assign ranks so that you can do like all reduce cleanly and properly. The nice thing about the rendezvous is that you can deploy it anywhere. So PyTorch Elastic now is integrated with Kubernetes and AWS without requiring the changes in the underlying infrastructure for the scheduler itself. So there's a nice feature. You can run your model with PyTorch Elastic and run essentially everywhere. So PyTorch Elastic addresses the resiliency problem, an elasticity problem. But how about big model problem? Models that doesn't fit in a single machine anymore. You want to split your model with some sort of model parallelism, and you want to support like huge parameters. This is particularly important for something like ranking and recommendation models. PyTorch RPC essentially enables you to write code that runs under multiple machines, but write it in a way that you're writing as if you're writing in a single machine. I'm going to show you an example shortly, but let's go into the key components of PyTorch RPC. RPC are there's the RPC layer, which allows you to run code on the remote machine. There's a second layer, which is the remote reference, which allows you to track or reference a remote tensor that doesn't exist in your machine. It's the remote machine. We do the garbage collection for dangling references behind the scene. The third feature is the distributed autograph. One cool feature about PyTorch for people who actually use is that you could write a backward path and then PyTorch automatically computes you could write the forward path and the PyTorch automatically computes the backward path for you. So this works great if you're on a single machine. Distributed autographs enables this to happen when you're writing remote tensors and RPC calls. We're going to take a close look at to see how this works. The fourth feature is the distributed optimizer, which works the same way, but these optimization functions need to collect all weights and compute the loss function. So let's look at the primitives for the PyTorch RPC. There are 3 simple primitives. First primitive is a synchronous RPC call. So you can call a synchronous RPC call to compute something on a remote machine, and you wait for the results. Then you can use this tensor result. The second one is the synchronous call. So the second one is an asynchronous call. So you can call something asynchronously. It gets you a feature that is available for you later whenever you need it. And the third one is a remote reference. So let's look at an example. You see, we are dividing 2 nets running on remote workers, and then we are writing our program, the optimization step. We're writing as if we are running on a single machine, and all we need to do is a magic step, which is number 3 with the distributed autograd context, and the computer distributed autograd for you automatically, and it computes everything automatically, and the rest of the steps is no different than writing a PyTorch program on a single machine. So what's happening behind the scene? Let's take an example. Here you have 2 tensors, T1 and T2. You want to add them together, but you want to add them together on a remote machine. So this happens in a worker number 1, and then you want to take 2 tensors, T4 and T5, randomize them, and then compute the loss. So PyTorch distributed, what it does, it inserts automatically send and receives calls for you and compute the gradients, knowing that this graph is partitioned across different nodes. So all you need to do is, like I said, a magic word with this distributed autograd context, and then everything else works automatically. We can do a lot of optimization with this thing as well. What we shipped is a fast mode, but this fast requires basically like the send and receive gradients to be computed in all the backward paths. But you can imagine we can optimize cases where we don't need to compute gradients for dangling pointers. Like for example, if you're doing a backward pass on the loss function, you only need to update the relevant parameters that correspond to this loss function computation and nothing else. So this concludes my talk. I want to end by call to action. Really excited that there is a lot of contributors across the industry, and it's available across different cloud providers, and it's really easy to use and has great documentation. So please try it out and let us know how it is. Thank you so much.